4.2, graph exponential decay functions. So in 4.1, we've been working on exponential growth function, which means every year, either the amount of bacteria or number of bunnies or the money you have in the bank grows exponentially because your base is a number bigger than 1. In section 4.2, we're going to have exponential decay because the base in our exponential function is now between 0 and 1, which means every time the x increase by 1, you divide the output by the value b. And you can see that the graph is a horizontal flip of the exponential growth function. Looking at example 1, you'll see that by plugging in the value, basically what you're doing is you will still have 1 as your y-intercept, because anything to the power 0 will give you 1. However, when you go to the right, instead of multiplying by 2, you're now dividing by 2 because the base is 1/2. But that also means that when you go backward, you're dividing by a 1/2, which means you're multiplying by 2. So this is a perfect flip horizontally of the exponential growth function. Why don't we take a second and think about why that is? Why is it a horizontal flip over the y-axis? This function right here can actually be written as 1 over 2 to the x, which is also equal to 2 to the negative x. Notice the difference between these two is actually simply the negative in front of the x, which means these two are horizontal flip of each other. We have not done much with horizontal flip, so you don't need to think about how they are flip of each other. You only really need to worry about the AHK model that we've been working on for 4 chapters now. But just want to give you an idea why using the property of exponent to explain why these two functions are horizontal flip. Moving on. Using transformation. So this section you'll see that is pretty much a mirror of the last section in 4.1. When you graph the function, again, all I expect from you is be able to go from the parent function, which is still 0, 1 here, and be able to multiply it by 2, which means it's a vertical stretch by 2 units. This also means that the asymptote is still y equals to 0. It's your asymptote, which means your domain is all real numbers and your range is y greater than 0. For b, we still have an exponential decay function. We're going to flip it because it's negative. We're going to multiply it by 1, 2, 3, which means this is our final function. Go ahead and pause the video now and try number 2, and then you can press play on the video again to see the solution. So here's the solution for number 2. Again, because b is less than 1, therefore I have an exponential decay function with a y-intercept at 0, 1, a horizontal flip because of the negative, and then multiply by 2 to give the vertical stretch. And here is our final graph. Example 3 has also the h and k shift. So you'll see that first they have they didn't draw the parent function, but they go straight to the parent function of 1/2 to the x power stretched by 3. So this graph right here, the blue line is the parent function stretched by 3. And then they did the horizontal shift by 1 unit because h is -1, and then down 2 because k is -2, and you end up with the red curve. So pretty straightforward, just like the last section. So if you know 4.1 well, 4.2 is just as easy. Instead of exponential growth model, when you apply in real life, you'll be doing the exponential decay model. In this case, you still have the initial value, which is a. And instead of adding a rate, you're going to do 1 minus r to the t power. Notice that with decays, you rarely talk about compound decays, so you will not have to worry about the n term as in compound growth. So in the example I gave in class, where I'm standing, let's say, 20 feet away from the classroom, you would say that distance from the classroom is equal to 20 feet, and every time I'm walking, decreasing the distance by half, so you're going to minus 50%. And t is the amount of time I take this, cut the distance in half, which means my final function is 20 times 1 minus 0.5 is 0.5, which means it's 1/2 to the t power. And this would be how you would write the exponential decay function for my distance to the wall in the classroom. So when t is 0, I have 20 feet away, that's where it begins. When t equals 1, I now end up at 10. When t equals 2, I'm at 5. When t equals 3, I'm going to be at 2.5, and so on. Here's an example from the textbook. A new snowmobile costs $4,200. The value of the car decreased by 10% every year. So you have the basic model, you put in the initial value, and the decay, which means every year you only are left with 90% of the original value. After 3 years, you take it to the third power, and the answer is $3,061.80. Let's go ahead and have you try number 6. When we're ready, you can pause the video. When you're ready, you can press play to see the solution for number 6. So here's number 6. We first begin with the parent function, which is still exponential decay. Again, is because b is less than 1. And then you do the horizontal flip because it's negative. Horizontal shift because it's 3. So this point right now is 0, -3. I'm going to move it 5 points to the right, 4 points up to this point right here, which is 4. Sorry, that's not a 4. That's a 5, 1 is my point. My asymptote used to be at y equal to 0, but that also got moved up 1, 2, 3, 4 units. This is my new asymptote. Which means my graph is now, I'll use blue, my graph is now over here. Here's your homework for 4.2. I will give you time during class tomorrow to work on this. And if you have any questions, feel free to ask me in class. Thank you for watching.